All right. So where we left off yesterday was we started to practice how to calculate out z-values, and then also knowing these z-values, we could figure out what percentage of our bell-shaped and symmetric distribution fell within the range of certain z-values. So let's try to jog our memory again. Why is a z-value? What's a z-value? So suppose I told you that you had a z-value of 1. What would that tell you?
It's one standard deviation away from the mean.
It's one standard deviation away from the mean, and more specifically, it's one standard deviation above, because it's positive, right? So therefore, if we had a z-value of negative 1, it would be one standard deviation away from the mean, but one standard deviation below the mean, right? So therefore, a z-value is nothing more than how many standard deviations you're away from the mean. And if you have positive z-values, you're going to be above the mean. If you have negative z-values, you're going to be below the mean. Right? Is everybody good with that? All right. So then we said, all right, we're going to go certain standard deviations. Right now we're still working with whole standard deviations. We're going to go certain standard deviations above the mean and certain standard deviations below the mean. And now what we're going to try to do is we're going to try to figure out what percentage of our distribution or what percentage of the data is between those two z-value cutoffs. Well, since we're working with a bell-shaped symmetric distribution, we learned a very, very important rule about the bell-shaped symmetric distribution last class. What was that important rule that we learned called? It's the empirical rule, right? The empirical rule. And what did the empirical rule tell us? Exactly. 68, 95, 99.7. Those are like the three important numbers I told you guys you should remember. And what 68% represented said that if we go one standard deviation above the mean and one standard deviation below the mean, then between those two cutoffs, we had 68% of the data. If we go two standard deviations above the mean and two standard deviations below the mean, then we're going to have 95% of our data. But if we go three standard deviations above the mean and we go three standard deviations below the mean, then in between those two cutoffs, we had 99.7% of the data. Then another thing that we did last class was we said, hey, I get the fact that we go 68, 95, 99.7, but we also know that this distribution is symmetric. So if we just look at this 68% range, and we divided that 68% range in half, then we said that on one half of that 68% range, we're going to have 34% since it's symmetric. And on the other half, we're also going to have 34% for a total of 68%. Right? Does everybody remember that? And then we also broke it up into these additional slivers for this, just this sliver right here of the distribution had 13.5%. Here, this sliver has 2.35%. And from here on to positive infinity, right? Just to make sure that everybody's well aware with that. This distribution does not stop right here. Technically speaking, it keeps on going on forever and ever and ever. But it gets closer and closer and closer to this bottom axis, which you can think of as the x-axis. Keeps getting closer and closer and closer to this axis, but it never touches it. Does anybody know what the term is called whenever two lines get closer and closer and closer, but they never touch? Anybody remember what that's called? It starts with an A.
Asymptote.
Yeah, it's an asymptote. Awesome, great. So whenever two lines get closer and closer and closer to each other, but they don't touch, then one of them is called an asymptote. So here, the asymptotes, these two things are asymptotic. So here the x-axis acts as an asymptote. So here this keeps on going then on to infinity. Here this one keeps on going down to negative infinity. Or, as Buzz Lightyear always likes to say, to infinity and beyond, right? All right, no, maybe not. Some people are just like, quit watching movies with your kids. All right, everybody good with the fact that here we have these percentages as well?
I've never seen a single Toy Story.
Say what?
I don't think I've ever seen a single Toy Story.
What?
I don't remember.
What? No Toy Story? To be honest with you, I've never seen a whole Toy Story movie either. right? Just like little
I might have
bits and
don't
pieces.
remember.
Yeah, it could have been a long time ago. All right, cool. Is everybody good with where we left off so far? So then all we're really doing in these examples right here is we're establishing different z-value cutoffs, and then we're going to find out what percentage of the data is in between those two z-value cutoffs. So we did the first example last class. Now we're going to do this next example here. So let's first do this one together. Consider a bell-shaped symmetric distribution with a mean of 800 and a standard deviation of 100. Approximately what percentage of the data is between 900 and 1,000? So just like we did last class, if you draw yourself a picture, it's going to help you out tremendously. So we know that we're dealing with a bell-shaped and symmetric distribution. So we have a bell-shaped and symmetric distribution. We have a mean of 800. So where on our bell-shaped and symmetric distribution are we going to annotate 800? Right in the middle, right? If it's the mean, we know for bell-shaped symmetric distributions that the mean is equal to the median, which is equal to the mode. So here then we're going to have this distribution centered on 800, and we're going to have a standard deviation, which again I'm abbreviating as std.dev. This is going to be equal to 100. Now we want to find out what percentage of our data, or of this distribution, is in between 900. So here I'm going to annotate 900, which is clearly above 800, to 1,000, which is right here. So we're going to try to find out this shaded region right here. Everybody good so far with the setup for this problem? All right, so we're trying to find out what percentage of the distribution is between these two cutoffs right here. Then one of the things that we can realize is that chances are, by just looking at this, we realize how many standard deviations is 900 away from 800. Just one, right? And how many standard deviations is 1,000 away from 800? Two, right? So here we're going to go one standard deviation above, and here we're going to go two standard deviations above. So therefore, what's the z value going to be for 900? And what's the z value going to be for 1,000? 2. Cool. So let's go ahead and do that just to make sure that everybody's on the same page with how to calculate out z values again. Here we're going to calculate out the z value of 900. And again, I just like making this 900 as a subscript. This is really just one of my habits. You don't have to do it that way if you don't want to. But it helps me keep track of what I'm trying to figure out. So we're trying to calculate out the z value of 900. Again, we don't know whether this is a sample or whether it's a population. So we could use either formula. I'm just in the habit of using the population formula for z. So that's why I'm writing x minus mu over sigma. We know that we're trying to find the z value of 900. The mean we said was equal to 800, or mu is equal to 800. And our standard deviation sigma is going to be equal to 100. So therefore we know that this is going to be 100 over 100. So just like we said, we're going to have a z value of 1. We try to find the z value of 1,000. Then again, using x minus mu over sigma, we're going to have 1,000 minus 800 over 100, or again, 200 over 100. So like we correctly said, our z value for 1,000 is going to be equal to 2. Well, now the question becomes is, between a z value of 1, so I'm going to bleed down here into this b part, and a z value of 2, we're trying to figure out what percentage of our distribution is between a z value of 1 and a z value of 2. Well, according to the empirical rule, and we did what we did last class, what percentage of our distribution is between those two cutoffs? 13.5%. So this we can get as 13.5%. So again, really briefly, just to make sure everybody's on the same page, since this is the first example that we're doing today. Here, if we go one standard deviation above the mean, so where we have a z value equal to 1, and if we go two standard deviations above the mean where we have a z value equal to 2, then between this cutoff right here and this cutoff right here, just like we calculated out last class, was equal to 13.5%. So that's why that's the answer to this question. Everybody good with 2A? Any questions about 2A? All right, then if we do 2B, Here, approximately what percentage of the data is below 600? So again, starting off with our picture, we again have a distribution centered at 800. Again, have a standard deviation of 100. Now we're looking to go below 600. So we're looking for this shaded region right here. Everybody good with this being the correct graph for 2B? All right, so then what we're going to try to do next is, what's going to be our next step? Convert it to a z-score, right? Because if we know our z-score, then we can take it to our empirical rule graph, and we can start looking at percentages there. So we're going to try to convert 600 into a z-score. So again, we don't know whether this is a sample or a population, so I'm going to use the z-value formula for a population. Again, you could use the one for a sample, whatever your preference is, it really doesn't matter. For this problem, I like using this population one. So again, we're going to have 600 minus our mean is 800 divided by 100 for our standard deviation. So therefore, our z-value is going to be equal to what? -2. All right. Now, what we're asking then is, we're saying that this 600 has a z-value that is equal to -2. And we're trying to figure out what percentage of our data is below -2. Well, again, going to this graph that we already figured out last class. Here we have a z-value of -2. And we're trying to figure out the percentage of our graph that is below this cutoff right here. Well, below this cutoff right here, we don't just have this 2.35% because that's just in this sliver, but we also have this 0.15%. And like I said at the beginning of class, this goes from here all the way down to -infinity. So therefore, how are we going to figure out what percentage of our data is below a z-value of -2? What are we going to do? Combine these two right here, right? 2.35 plus 0.15. What does that come out to be? 2.5. So we're going to have 2.35% plus 0.15% is equal to 2.5%. Any questions about 2B? Or not 2B? Yep. Another quirky joke for today. Gotta fit one in about Duke sometime, huh? I'm off to a roll already. Any questions about these examples, huh? All right, then take about 2 minutes or so for yourself and see if you can answer question number 3A and 3B by yourself. Whenever we're dealing with a bell-shaped and symmetric distribution, we're always going to use that.
Okay, with the same percentages and everything on
Yeah, like the 68, 95, 99.7 that you see right there.
Yeah.
Those are like the empirical rule.
Okay.
So those are like three percentages that's really, really, really important for you to memorize.
Right.
So that whenever it says you have a bell-shaped and symmetric distribution, you know that those 3 percentages are always going to apply to that thing.
Okay.
And then what we did last class was we took those 3 percentages and we just broke them apart into those slivers.
Mm-hmm.
So what I said last class is that the people who tend to do well on like the first exam, because you're going to have to do a bunch of these on the exam, right?
Okay.
Is if you remember those percentages, like in the individual slivers. If you remember these percentages right here, 0.15, 2.35, 13.5, and 34, and these right here are just the same thing because this graph is symmetric. The people who do really well is like as soon as they get the test, they draw this graph at like the top of the test, and they write down these percentages, because as you can see, all the So you're always going to have to know what percentages are just in these individual slivers.
Right.
So if you know those, you can just keep referring back to that graph.
Can I take a picture of that?
Yeah, of
I'm
course.
just like,
Yeah.
I'm scared.
Sure can. Here, let me scroll it down a little bit so you get the whole thing.
Thank you.
Yeah, how's that look?
Perfect. Okay, thank you.
Sure.
And I just have a question.
Sure.
Are you going to give us what questions we should study, or do you want us to pick it out, like on the common final exam?
So I can show you guys which questions apply to which chapters.
Okay.
Do you have that past common final exam booklet with you?
Yeah.
So how about like the last 5 minutes of class? I'll do it up here on the document so everybody can see.
Okay, perfect. Yeah.
Cool. Anybody need any extra time to work on 3A and B? Right. Then let's do it. So again, consider a bell-shaped symmetric distribution. Again, if you draw yourself a picture, the pictures always help. Now we have a mean of 500. We know for a bell-shaped symmetric distribution that the mean is right in the middle. And a standard deviation of 200. Oh, I'm sorry, of 20. Approximate what percentage of our data is between 440 and 480? So we're going to try to find this shaded region right here. Is everybody good with that? What's going to be our first step? Finding the z-scores of both 440 and 480. So we're going to have the z of 440 and the z of 480. Again, we don't know whether or not it's a population or it's a sample. So I'm just going to use the z-value formula for a population. Here we have that the that the x value is 440, our mean is 500, and our standard deviation is 20. So here we're going to have negative 60 divided by 20, which is equal to negative 3. Everybody good so far? Everybody on the same page? Then here we're going to have 480 minus 500 divided by 20. And here this is going to be negative 20 divided by 20. And that's going to be equal to negative 1. So then we're trying to figure out what percentage of our data is between a z-value of negative 3 and negative 1. And the answer to that is 15.85. So here, 15.85%. And how do we get 15.85%? Again, if we go back to our graph, going down to a z-value of negative 3, we're right here. A z-value of negative 1, we're right here. In between these two cutoffs, we have both 13.5 and 2.35. So here then we're going to have 13.5% plus 2.35%. And if you do the arithmetic correctly, you correctly end up with 15.85%.
Are you always going to add those, or like on the other side, do you subtract them, or you just always add them?
You always add them, right?
Okay.
So, in these problems is this. We know that 13.5% of the data is always in this sliver, right? Same thing with 13.5% of the data is always between this sliver. So if I said, hey, tell me what percentage of the data is in this sliver plus the percentage of the data that's in this sliver, well then you would just take 13.5 plus 13.5 over here. Right? You go with that? So whenever it saying, hey, find the data that's in these slivers, you're always going to take all those and you're always going to add them together.
Okay.
What you're trying to find. Does that make sense?
Yes.
Cool. Yep. Good question. Any other questions? All right. Then for B, we have approximately what percentage of the data is above 540. So again, here we have 500. Standard deviation is 20. We're going to go up to 540. Saying above 540, so now we're looking at that shaded region right here. We're going to find the z value of 540, which x minus mu over sigma is equal to 540 minus 500 divided by 20, which is going to give us a positive 2. And what percentage of the data is above a z value of positive 2? 2.5%, right? Because again, we get 2.35% plus 0.15% is equal to 2.5%. Is everybody good with how to get this 2.5% right here? Any questions whatsoever? Everybody's good with these three examples? So these are going to be the types of problems that you're going to have to do on your homework assignment and on the test. The only difference between the questions on your homework assignment and the test and these examples that we did right here are the questions on your homework and on your test usually just add some additional words to the problem, right? Like it might say something like this. It's going to say, let's say that the number of calories that you eat for lunch has an average of 500 calories. And each meal that you have has a standard deviation of 200 calories. You guys see right there? I'm giving you the numbers, but I'm just saying, hey, these things are calories, right? I'm just adding more word to it. Or the way that I like to say it is I'm making these problems a little bit more flowery, right? Like I'm adding more fluff to stuff. But essentially what you're always trying to pick out is you're always just trying to pick out which value you're using for x, what your mean is equal to, and what your standard deviation is equal to. And if you can pick out those three numbers, then you just plug those into your formula and you can calculate out your z values and use the empirical. How do you guys feel about all that stuff so far? Good? Awesome. All right, then let's move on. The last thing that we have to do to finish up Chapter 2 is talk a little bit about Chebyshev's theorem. Chebyshev's theorem. So Chebyshev's theorem, sometimes you see it spelled a little bit differently. Sometimes you see it spelled as Chebyshev's, or sometimes you see it spelled as Chebyshev's. It's just a whole bunch of different kind of spellings between SH's and CH's, primarily because Chebyshev was a Russian mathematician, and the Russian alphabet is a little bit different than the alphabet that we use, but it's pronounced Chebyshev's. So Chebyshev's theorem. What does Chebyshev's theorem tell us? Well, as you can see from this picture, right, so I'm going to go over what all this definition right here says, but we're going to do it in terms of a picture down here. Just looking at this picture, what's the main difference between Chebyshev's theorem and the empirical rule? Right? This right here is definitely not a bell-shaped and symmetric distribution, which means that Chebyshev's theorem we can apply to any distribution. It does not have to be a bell-shaped and symmetric distribution, right? So this applies for any numerical data set or any distribution that we create from this numerical data set. It's absolutely anything that we want to apply this to. So let me ask you this. Can we apply Chebyshev's theorem then to a bell-shaped and symmetric distribution? Yes, right? Because a bell-shaped and symmetric distribution is a data set. This works for any data set, so therefore we can also apply this to a bell-shaped and symmetric distribution. Can we apply the empirical rule to a distribution that looks like this? No, we can't, right? Because the empirical rule only applies to a bell-shaped and symmetric distribution. So because the empirical rule only applies to a bell-shaped and symmetric distribution, we cannot apply the empirical rule to a distribution that looks like this. Right? Is everybody good with that? So it goes one way, but it doesn't go the other way. Right? All right. So whenever we have any distribution, we can apply Chebyshev's. Now, as we're going to see once we go a little bit more through Chebyshev's, Chebyshev's is a little bit less accurate than the empirical rule is, right? Especially for a bell-shaped distribution. So therefore, if you have a bell-shaped distribution, in this class, you have to use the empirical rule because it's just a little bit more accurate, right? So if you have a bell-shaped symmetric distribution, you have to use the empirical rule, but theoretically, you could apply Chebyshev's theorem. But if you apply Chebyshev's theorem to a bell-shaped and symmetric distribution in this class, you're going to get the question wrong. Cool? Everybody good with that? All right. So let's talk about it. What Chebyshev's theorem tells us is this. Chebyshev's theorem uses a formula, and this formula that it uses is 1 minus 1 over k squared. 1 minus 1 over k squared. And I do not believe that this formula is on your formula cheat sheet, right? So I don't think that this one's on there. So therefore, this is a formula that you're going to have to memorize. Or like I've said now a couple times in the past, you can also just store it in your calculator, right? 1 minus 1 over k squared. So let's see what this formula means. First off, this little k you can think of as being an equivalent to our z, right? So all the z's that we used before is like the cousin of this k value. So these things are kind of like cousins. Now, what do I mean with that? First off, what does a z value represent again? The number of standard deviations we're away from the mean, right? The only time we ever use z values is if we have a bell-shaped and symmetric distribution, right? That's the only time we've used it so far in this class. That's the only time we're ever going to use it in this class. The only time we're ever going to use z values is if we have a bell-shaped and symmetric distribution. Right? Is everybody good with that? But here we don't have a bell-shaped and symmetric distribution for Chebyshev's, but we still want to know how many standard deviations we're away from the mean. So therefore, if we still want to know how many standard deviations we're away from the mean, but we can't use z, we're going to use k instead. So therefore, k is the same thing as the number of standard deviations away from the mean. So now instead of using z to talk about this, we're just using k to talk about this. In statistics and mathematics in general, we always want to be very, very specific about what we're using. So therefore, now that we're using something slightly different for any distribution than what we were doing for whenever we just have a normal distribution or a bell-shaped symmetric distribution, we're introducing a new symbol, k, but k is essentially telling us the same thing. Right, is everybody good with that? All right. So here, this is what Chebyshev's theorem tells us. The number of standard deviations that were away from the mean, we're always going to plug that value into k. Now, here's an important difference between Chebyshev's theorem and the empirical rule. In the empirical rule, we sometimes went 2 standard deviations above the mean, where we had a z value of 2. And then the other cutoff was like 1 standard deviation below the mean. So we had a z value of -1, right? Is everybody good with it? Like in all those examples that we just did, sometimes we had 3 and 1, sometimes we had -1 and -2. We had different values for our different cutoffs. You cannot do that with Chebyshev's theorem. In Chebyshev's theorem, if you go 2 standard deviations above the mean, you have to go 2 standard deviations below the mean. If you go 3 standard deviations above the mean, you have to go 3 standard deviations below the mean, right? So their k values have to always be the same number, except one of them has to be positive and the other one has to be negative. Right? Is everybody good with that? So that's for k. That has to apply for k. So, and whatever that is, whatever number that is, we can plug that in for k. So if we go 2 standard deviations above the mean, and we go 2 standard deviations below the mean, so here then k would be equal to 2, and here k then would be equal to negative 2. Right, is everybody good with that? We plug that value into this formula for k. Now, does it matter whether we plug in positive 2 or negative 2 into this formula? Why does it not matter? Because we're squaring it, right? So you can say, hey, I'm going to take positive 2 and stick it in here. Or you can say, hey, I'm going to take negative 2 and I'm going to stick it in here. It doesn't matter. Since we're squaring it, we're always ending up with the same thing, right? So let's do that. Let's suppose that we go 2 standard deviations above the mean, and suppose we go 2 standard deviations below the mean. Then what we're going to have right here is 1 minus 1 over 2 squared. Right, I'm plugging in 2 now for k. Now this is going to be equal to 1 minus 1 over 4. So that's going to be equal to what? Yep, it's like 3/4, which is just the same thing as 0.75. Right? And that's exactly what it says up here. Between these two cutoffs, we have at least 0.75 of our data. Right? Is everybody good with that? Everybody good with now how we got that 75% or 0.75? Is everybody good with, and this is something that I probably should have asked a little bit more explicitly a couple of classes ago, is everybody good with going from fractions, like 3/4, to a decimal, like 0.75, to a percentage, like 75%? Is everybody good with converting between those three things? All right, cool. So is everybody good then with how we got this 75% right here? All right, so then let's try to figure out how we got this 88.89% right here. Well, first off, how many standard deviations are we over here? 3. So therefore, our k right here is going to be equal to what? Awesome. How many standard deviations are we away over here? 3. So therefore, our k is going to be equal to negative 3. Right, is everybody good with that? So we have 3 and we have negative 3. That's always the first stop where we want to stop and we want to say, hey, are these two numbers the same, but one is positive and one is negative? Sure is, so we're good to go with using Chebyshev, right? So now what we're going to do is we're going to plug in 3 or negative 3 into 1 minus 1 over k squared. So that's going to become 1 minus 1 over 3 squared, which is equal to 1 minus 1/9, or 8/9. And if you do the arithmetic on 8 divided by 9, you end up with 0.88888888 repeating. Or if you round it to here, we're going to end up with 0.8889. Everybody good with 0.888889? So then again, if we convert this into a percentage, we get 88.89%. Everybody good with how we're getting these percentages? All right. So now let me say this also. In Chebyshev's theorem, we don't have to stop at k being equal to 3 or k being equal to negative 3, right? What we could now do is we could go to k to 4 and k negative 4, or 5 and negative 5, and so on and so forth, right? We're just going to keep increasing the number that we have in our formula for k. So therefore, we're going to get a percentage that keeps getting closer and closer and closer to what? Not 0. 100%, right? Because what we're saying is that, hey, between a cutoff way over here and a cutoff way over here, at least what percentage of our data is between those two cutoffs? Well, we're getting closer and closer and closer to 100% of our data. Right? Does that make sense? All right. The other thing that I want to point out, and this is a very, very, very important but often missed difference between the empirical rule and Chebyshev's theorem. If you look back at the empirical rule says that we have approximately 68% right here. We have approximately 95%. And we have approximately 99.7%. Even up here in the wording of these definitions, we always have approximately. That is different than Chebyshev's theorem. in Chebyshev's theorem, we always have at least this percentage. At least this percentage, right? So we have at least, at least, at least. Right? Does everybody see that those two differences? So why is that so important? Why am I pointing that out? Well, let's do this. If you go one standard deviation above the mean here, and you go one standard deviation below the mean here, what is the k value going to be for this upper cutoff? And what's the k value going to be for this lower end cutoff? -1. All right. See what happens whenever you plug in 1 or -1 into this formula right here. 1 minus 1 over k squared. What do you end up with? 0. It's 0, right? So here if we have 1 minus 1 over k squared, and we plug in positive 1 in for k, now we're ending up with 1 minus 1, which is just 0. 0%. So what is Chebyshev's theorem telling us? It's not that it's impossible to measure.
It's an approximation.
It's an approximation. What's the approximation saying?
It has to be at least 0%.
Yeah, right? So Chebyshev's theorem is telling you this. It says, hey, if you go one standard deviation above the mean, and you go one standard deviation below the mean, in this sliver right here, doesn't matter what your distribution is, you're going to have at least 0% of the data. To which you say, thanks, Chebyshev, right? Tells you nothing, right? But you guys see the difference between the wording for the empirical rule and for Chebyshev. Here, it's giving us like a lower bound. It says you need to have at least 0%. You need to have at least 75%. You can have more, right? And in fact, in the empirical rule, we do have more. Because in the empirical rule, we have 68% between these two cutoffs. But is 68% at least 0%? Sure is. Here, Chebyshev's theorem is telling us between these two cutoffs, we need to have at least 75%. Well, if we go between these two cutoffs on the empirical rule, we have 95%. Is 95% at least 75%? So you guys start to see that I'm saying that the empirical rule is a little bit more accurate whenever we have a bell-shaped and symmetric distribution. Because we know that it's not just at least 75%, we know that it's approximately 95%. Is everybody good with that? Cool. All right. Is everybody good with the differences between the empirical rule and Chebyshev's theorem, and when we apply the empirical rule and when we apply Chebyshev's theorem? All right. Then let's practice applying Chebyshev's theorem. If you look at these next three examples in the notes, you'll notice that they look really, really, really similar to the examples that we did previously with the empirical rule. With one very, very, very important difference. If you look at question 1a, what's the important difference for this example than we did whenever we were doing it for the empirical rule? We have a skewed left, right? It says consider a skewed left distribution. So therefore here, we know that it's not bell-shaped and symmetric. If we have a skewed left distribution, which direction do we have then the fat tail of the distribution? On the left, right? So generally speaking, if you want to picture this, a perfectly fine example to think about for a skewed left distribution is a distribution that looks like this, where the fat tail of the distribution is over here on the left-hand side. So if you're trying to picture a skewed left distribution, this is a perfectly fine example. All right, so let's do this one together. Suppose that we have a skewed left distribution, so let me redraw it down here. We have a skewed left distribution with a mean of 2,400. So now we have some average. I don't really know where this average is. I'll just say that randomly I'm going to put this average right here. With an average of 2,400, and again we have a standard deviation of 200. Now again, it's asking us at least what percentage. So again, that's another clue for the fact that you're using Chebyshev's theorem, right? Now you don't just have a skewed distribution, but it's also asking you at least what percentage. of the data is between 2200 and 2600. So now instead of calculating out a z value for 2200, we're going to calculate out a k value for 2200. And instead of calculating out a z value for 2600, we're just going to calculate out a k value for 2600. Basically, if you follow the same steps for these examples, like I showed you the steps for the previous examples, you're going to get these questions right? That's why all of these examples, I'm always following the same steps. If you get in the habit of doing what I'm doing up here, then you should be good. Now, the good thing is that we're just trying to find out how many standard deviations our cutoff, our x value, is away from the mean. So therefore, again, we can simply just use the formula x minus mu over sigma, because we're trying to figure out how far away a cutoff is from the mean, and we want to express that in terms of standard deviations. So the formula is even the same, right? So literally the only difference is we're swapping out k for z. All right. Well, here then we're going to have 2200 minus 2400. Confused myself there for a second. Divided by 200. So here we're going to have a k value of -1. Then for 2600, we're going to have 2600 minus 2400 divided by 200. Here we're going to have a k value of 1. All right. Now, an important step always to realize is this. Are these two values, -1 and 1, are these two values the same except one is negative and one is positive? Yes. Only if you answer yes to that question are you allowed to apply Chebyshev's theorem. If this was -1 and this was 2, your answer simply is cannot be determined. You have to stop there. Right? Is everybody good with that? All right. But here we have the same k value. So therefore, what is our next step going to be? Awesome. So now we're going to have 1 minus 1 over k squared. Again, it doesn't matter whether or not you plug in +1 or -1 in for k, since we're squaring it. So we're going to have 1 minus 1 over 1 squared, and this is going to be equal to 0, or simply just 0%. That didn't work out. Let me try that again. 0 or 0%. So according to Chebyshev's theorem, according to Chebyshev's theorem, at least what percentage is between 2200 and 2600? At least 0%. Everybody good with this? All right. Then let's do this. Let's do B. Again, we have a bell-shaped and symmetric distribution with a mean of 2400 and a standard deviation of 200. And it's asking us to figure out what percentage of our data is above 2800. So we're trying to find this shaded region right here. What do you guys think about that? What would we do next?
Could it technically not be determined?
Why is that?
Because we don't have two numbers.
We don't have two numbers, right? Just like we went back here, I said the important consideration is that these two numbers are the same. It's just that one's negative and one's positive. Mm-hmm. But here, if we calculate out a k value for 2800, we're going to end up with something. But what do we compare that to? There's nothing to compare to. So is it possible to have the same numbers, but one is positive, one is negative? It's not possible to have it. So therefore, this right here cannot be determined. Is everybody good with why this cannot be determined? We need to have two cutoffs. We need to have two k values. And those two k values, one of them needs to be positive something, the other one needs to be negative something, where the something is the same. But here we would only ever get one k value, so we would never have that second value. Right, is everybody good with this? All right. Then take maybe 2 or 3 minutes or so for yourself, and see if you can do 2A and 2B by yourself. I missed somebody on my attendance. Is Justin here? Is Jay here? Is Joseph here? Is Sarah here? And is Tyler here? Sorry about that, Tyler. Does anybody need a little extra time? Everybody's good to go? Alright, then let's do this one. So now we have a skewed right distribution. So again here, a perfectly fine example to imagine is one that has a fat tail over here on the right. Here we have the mean of 300 and a standard deviation of 30. We want to figure out at least what percentage of the data is between 240 and 360. So here we're going to calculate out k value of 240. Here we're going to calculate out a k value of 360. Again, the formula is essentially the same for a z value. You can again either use the one for a sample or for population. I'm using the one for the population. So then we're going to have 240 minus 300 divided by 30. So here we're going to have a k value of -2. Then here we're going to have 360 minus 300 divided by 30. So here we're going to have a k value of. Can we use Chebyshev's theorem for this? Absolutely. So what's our next step going to be? What value are we going to plug in for k? 2 or negative 2, right? It doesn't matter. It's always going to be the same thing. I like 2. So then here we're going to have 1 minus 1/4 or 0.75 or 75%. Everybody go with 75%? Any questions about 2A? Yeah.
Could you just refer to the sheet if you know how many deviations you have? Say if you have 2, can you just refer to this and see if it's at least 75%?
Yes. I think what you're asking me is this. If we go 2 above and 2 below, is it always going to be 75%? The answer to that is yes. Right? 3 above and 3 below, it's always going to be 88.89%. 4 above and 4 below, whatever number that comes out to be, it's always going to be that number. Yep, exactly right. Same thing with the empirical rule. If you go 1 above and 1 below, it's always going to be 68%. Same concept applies. Right? Go with that? Cool. Then here for B, we have a right-skew distribution, again with a mean of 300 and a standard deviation of 30. Below 210, we're looking for this shaded region. What do we know about that? Everybody good with the fact that it cannot be determined? Any questions about these first 2 examples? All right, this third example here, I'm going to change this from bell-shaped and symmetric. I'm going to change this to simply just having a skewed distribution. Or something that you might see on the homework, it might not necessarily say a skewed distribution. Like Betsy said, it might say that your distribution has no mode. Right? If your distribution has no mode, then again we have to apply Chebyshev's theorem. Does that make sense? If we have 2 modes, do you apply empirical rule or Chebyshev's theorem? Chebyshev's theorem, right? Because when you have 2 modes, you have 2 peaks that are the highest, right? You can have all sorts of stuff in between, but you're definitely going to have 2 peaks that are highest. If you just have 1 mode, do you apply the empirical rule or Chebyshev's theorem? Good. You don't know, right? If you just have 1 mode, right? Now, if you just have 1 mode, you most certainly could have a bell-shaped and symmetric distribution. But if you just have 1 mode, you could have a distribution that looks like this. So if you only have 1 mode, you don't know which one of these you have. So therefore, can you apply the empirical rule? No, you can't. But could you apply Chebyshev's theorem? You absolutely could, right? So if the only information that you're given is you have 1 mode, well, then you have to apply Chebyshev's theorem because you don't know that it's a bell-shaped and symmetric distribution. Right? Does that make sense? You had a question?
Notice in the homework it has proportion. Some has proportion, some has percentage.
Mm-hmm.
So just the difference of changing from one to the other.
Yeah, exactly. So a proportion is just what fraction of things you have, right? So if it says like your proportion is that 3 out of 4 things has some characteristic, and it's just talking about a fraction, so you can convert this then to a percentage or a decimal. Yep, that's exactly right. Yeah.
So the first thing we do when we see these problems is try to figure out which graph to use or which, and we can do that by looking at the modes or looking at the wording of it.
Yep, great question, right? So you're right. Our first step is always to say, hey, am I going to apply the empirical rule or am I going to apply Chebyshev's theorem? The only time that we can apply the empirical rule is whenever we have a bell-shaped and symmetric distribution. So it could say that your distribution is bell-shaped and symmetric. Well, whenever you have a bell-shaped and symmetric distribution, in this class, you should only apply the empirical rule. Right? Now, we also know that the characteristic of a bell-shaped and symmetric distribution, one characteristic that applies here is that we have the mean is equal to the median, which is equal to the mode. Right? So therefore, from this characteristic for a bell-shaped and symmetric distribution, we know that we can only have 1 mode. Because you can if we're calculating on an average of some set of numbers, we're only going to have one average. So therefore, if the average is equal to the mode, then we can only have one mode. Right?
Okay.
So if you're given the setup that you have a bell-shaped symmetric distribution, then you know that the mean is equal to the mean, which is equal to the mode. But if you go the opposite way around, if it says that you have two modes, right? If you have two modes, well, you can't have two modes then equal to one average. So therefore, if you have two modes, you know that it cannot be bell-shaped and symmetric. Right?
Okay.
You good with that?
Right, yeah.
So if you have two modes, you cannot apply the empirical rule. You have to apply Chebyshev.
Okay.
Right? Is that good? So really, the only time that you're ever going to apply the empirical rule is if it says you have a bell-shaped and symmetric distribution. Then you're going to apply the empirical rule.
Okay.
Every other time that you have, it's always going to be Chebyshev's theorem.
Okay, that makes sense.
Cool. Yep. Any questions? Any other questions? You guys good with this stuff? All right. Anybody want to do this last example then? All right. If I just scratch this out and call it skewed, what are we going to do? We're going to do Chebyshev's. We're going to find k's. We're going to see if the k's are the same. Plug k's into the formula. Down here it says that we're going to be above some value, so therefore we only have one cutoff, so therefore we're just going to write cannot be determined. Right, is everybody good with that? You guys get the gist of all these? Anybody want to do this last one? I'll gladly do it. No, everybody's good?
I think you can determine that.
Is that right? So here we're 2 below, yep, and here we're 1 above. So our k's would be different. Right? Is everybody good with that? So our k's would be different, so we couldn't apply Chebyshev. So it's cannot be determined here and cannot be determined here. Everybody good that both of them cannot be determined? Cool. And that's if I do this right here, if I scratch this out and I say that this is skewed. Bless you. All right, cool. So that is chapter 2. So now you guys are definitely going to be able to do your homework for chapter 2. Let me pause this video because we're going to go on and also do chapter 3. Right when I have that on a different video.